Let's illustrate the Bolzano-Weierstrass theorem here. This tells us that for any bounded sequence of real numbers, okay, real numbers has a convergent subsequence. Of course, previously we have identified that for any sequence, we can always come up with a subsequence that's actually given to us by the previously discussed theorems. And we're also able to establish ideas whether our subsequences are convergent or divergent, and etc. Just for this theorem, it doesn't tell us that the sequence is convergent. But we are assured of that if we have a bounded sequence of real numbers, it has a convergent subsequence. Let's illustrate this using an example here. Okay, we will have other video for the proof of the theorem. Here we'll just be illustrating that. Let us say our sequence x sub n, let's just say it's -1 raised to n. This is our sequence. Okay, so we can of course identify a subsequence to this, but we need to identify here, because this is existence, not just any subsequence, but they must be convergent. Previously, in our monotone subsequence theorem, in any sequence of real numbers, we can always come up with a subsequence that is monotone. Here, strictly, it should be convergent. But for convergent, we can use the idea of monotone actually. So for this, let me come up here with the first few terms or elements of the sequence. When n is 1, that's actually -1. When n is 2, that's +1. -1 for 3, n is 4 is positive. -1, +1. Okay, so this is our sequence. Now, looking into this, we can actually say that it is bounded because when you look into this, you can identify the supremum of this given sequence being the least upper bound. And for this, since it's an alternating sequence, its least upper bound is actually +1. Okay. And its infimum, which is the greatest lower bound, here, since again it's an alternating sequence, is -1. With this two already established, it has a supremum and an infimum. It is both bounded above and bounded below. Then we can say this is really a bounded sequence of real numbers. And since we have guaranteed the first part of our theorem, that is a bounded sequence of real numbers, we can actually identify here a convergent subsequence. Not just any subsequence, okay? Convergent subsequence. Let me come up here with this first subsequence. Let us say this is x of n of k, which is a result or a sequence of -1 raised to the power of 2n. Okay, all of its elements we will have here. When n is 1, it's +2, so that's +1. When it's 2, that's 4, 1, 1, and 1 here. Okay, so on and so forth. That's 1. Okay, looking into this, when you say convergent subsequence, the limit of the said subsequence should also exist. Okay, now take note here that this sequence here is not guaranteed to be convergent. So let's try to not to be confused with the subsequence convergence theorem, which tells us that the limit of the subsequences is equal to the limit of the sequence if the sequence itself converges to x. Here, there's no guarantee that the given sequence is convergent, so hence we cannot use a subsequence convergence theorem. To show that this is convergent, of course, we can actually look into the idea of the constant sequence. So the constant sequence, you have the same value, so the limit of this x sub n sub k is equal to 1, as this is the value or the constant value of the sequence. Since the limit exists, we can say that this subsequence is convergent. Okay, because the limit exists. But this does not necessarily tell us that this is also the limit of the sequence here. Okay, because we are not sure that the sequence is convergent. So we have now established the presence of a convergent subsequence for a bounded sequence here. We could also look into this if you would like to. The other subsequence, let's just say x of r of k, let's use negative 1 raised to the power of 2n plus 1, and the elements here are negative 1, negative 1, negative 1, negative 1 as well. So we can see that the limit of this subsequence is negative 1, and hence, and since the limit exists, this is also a convergent subsequence. Okay, now does this, as mentioned earlier, it doesn't, but does this tell us about the limit of this bounded sequence? Now there is another illustration for that, looking into the idea of limit superior and limit inferior as we will move forward to the next few videos. Just for the Bolzano-Weierstrass theorem, this tells us that once we have guaranteed that our sequence of real numbers being bounded, it has a convergent subsequence. Thank you very much for watching.